Think of this figure as a graham cracker with a bite taken out. Well, that didn't work. All right, let's understand what it means to find the area between two curves. To get this point across, I want to look at this figure right here. How would you find the area of this figure? How does this translate into the idea of area between two curves? Let's check that out. Visualize the rectangle, find the area of that rectangle, which is 28 square inches. Now visualize the circle being ripped out of that rectangle on one side. What we want to do is cut out this portion of that area, but we need to find that portion of the area. So what's the area of a circle? If we find the area of the full circle, we could divide that by 2, and that's the area that we're cutting out of that rectangle. The area of the circle is 2 squared, which is 4 pi. That's the area of the full circle. We're only taking out half of that from that rectangle. And therefore, the area of the semicircle is half of 4 pi, 2 pi. Okay, so now let's go back to the figure. The area of this figure right here would be the area of that rectangle minus the area of that semicircle. How does this translate into the idea of area between two curves? Let's check that out. That didn't work. Let's try it again. All right, find the area bounded between f of x is equal to 6x minus x squared and g of x is equal to negative x plus 6. Let's go ahead and plot these on one coordinate plane. Here are these two curves plotted on the same graph, just a rough sketch. We don't have to get everything perfect, but we do know that the quadratic passes the x-axis at 0 and 6, and the line has a -1 slope with a y-intercept 6, and therefore also has an x-intercept at 6. Let's visualize the area bounded between these two curves with this shaded region. Okay, that's the area that we're going to try to find. And so going back to the graham cracker idea, the rectangle with a semicircle bitten out of it, what we like to do is first find our limits of integration, and that's going to be where the two curves intersect. To find those 2 points of intersection, what you could do is just set the two functions equal to each other and find those x values. So let's do that very quickly right here. All right, there we go. F of x equals g of x. We set the two functions equal to each other and we solved. It turned out to be a quadratic that could be factored. And so the points of intersection are at x equals 1 and x equals 6. So let's go back to our picture and let's label that. We're going to integrate from 1 to 6. Now let's see why I started this video off with the rectangle with a semicircle cut out of it. Let's take that idea and apply it to this situation, because we want to find the area bounded between these two curves. If we can find the area under each one of these curves individually, then all we have to do is subtract one from the other, but we have to do it in the correct order. I have a short video linked in the description below using the Fundamental Theorem of Calculus to find the area under a curve, and a longer video linked in the description below that explains the limit definition of a definite integral to find the area under a curve. Feel free to check those out, but let's go ahead and separate these two curves and find their areas individually. Let's go ahead and use the Fundamental Theorem of Calculus to find the area under f of x from 1 to 6. I set up the definite integral. Now let's integrate. Okay, there's our Fundamental Theorem of Calculus being applied, and so the area under f of x from 1 to 6 is this. All right, let's do the same for the area under the curve of g of x from 1 to 6. I've set up the definite integral. Now let's apply the fundamental theorem of calculus, and it'll look like this. And so the exact area under the curve of g of x from 1 to 6 would be this. All right, now let's go all the way back up to the original, and let's find the area between these two curves. So let's visualize what we want to do. We want to take the area under f of x, which was all of this, remember that was 100 over 3, and then we're going to subtract the area under g of x, which was this, which was 25 over 2. So the area bounded between f of x and g of x would simply be 100 over 3 minus 25 over 2, which would give you 125 over 6. That's the area between these two curves. Now think about what we just did. We took one definite integral and subtracted another definite integral. So let's look at this same problem a little differently. I hope this visual representation helped. Okay, let's look at this just using integration instead of looking at it visually. We still need our two limits of integration, which were 1 and 6, but look at what we need to do. We want to set up an integral from 1 to 6, and we took the function that was on top and subtracted the function on bottom. So we don't have to break this up into two integrals. We could do it all together by doing the top function, which in this case was f of x, minus g of x dx. If you apply this property, f of x minus g of x, that'll look like this. And if you apply the fundamental theorem of calculus there, you will get 125 over 6. That would be the area between these two curves. I hope the pictures and the graham cracker analogy, or the rectangle with the semicircle cut out of it, help visualize what you're actually doing when you subtract the area under one curve from the area of another curve. If this video helped you out, please like the video, consider subscribing. Also, let me know in the comments if either something wasn't clear or if you want to see another example using this idea. All right, I'll see you in the next one.